use one of the open source freeware option here, UQLab, combined with my finite element software. So I use one of these, actually. As Johan just pointed out, when you are running finite element calculations, even if you have a very powerful computer, there is just no point of running 100,000 computations, right? So if I'm just coming back here, probably that's the only way of solving my problem is to use surrogate modeling or meta modeling or response surface. This is the same word for the same algorithm. So what do I do? First of all, I run 100 computations with 100 sets of samples. So you see, for instance, here, set number 6, you have a value for E1, a value for phi1, a value for C1, etc., for my 10 input variables, and I get an answer for the settlement, the maximal settlement of the silo. So I run that 100 times, and then using this meta model, I can compute a kind of a continuous approximation of the discrete 100 computations. And this continuous approximation is just an equation relating the input variables with the output results. And you can see that there is a measurement of the quality of this meta model. So this means that if 100 samples is not enough, maybe I have to run 50 more. But somehow, for the type of problems that we solve regularly, yeah, between 100 and 200 samples is enough to get a good meta model. And then when you have a meta model, this meta model is just an equation, so you can run that like 1 million times and then use the actual regular Monte Carlo simulation. First of all here, the sensitivity analysis. Remember, my engineering judgment told me that it would be probably soil number 2, which would be important, and my engineering judgment was obviously good. You see also that these, I just combine these three in just one geotechnical unit, but these three have very little to see with what happens here, and there is some kind of influence on the water level, which is not too, which is somehow logical. So this is for the sensitivity analysis, and it's also a good thing to do that, because if somehow you get these parameters which absolutely you don't understand why, so probably there is something wrong, either in the meta model or in the way that you have defined your limit state function. So it's always good to do sensitivity analysis. This could also imply that if I run other computations, I could probably set these parameters to either nominal or characteristic values and then redo the thing without too many probabilistic variables. Now, reliability analysis. What is the probability that my settlement of the silo is greater than 25 millimeters? Well, you can see here it's about 20%. So with my choices of probabilistic variables, with my choice of distributions, I have 20% of exceeding the threshold. So I go back to my client and I tell him that. Now what? Is it okay for him? Well, according to my target probability of failure, which we set together to be 5%, no, it's not okay. So what do we do? Either we change the design. Maybe one possibility would to add a blocking mat at the bottom of the excavation, so we don't excavate everything and then we do the mat. Maybe one way would be to leave berms and then excavate step by step, construct the concrete mat and see that. But of course this has a cost. So this is just the convergence, just to see that there is also a confidence interval between, maybe 21 and 18%, something like that. But I think Johan and Kerstin also talked about, and also Timo actually, everybody said the word Bayesian. So what is the Bayesian updating? It's somehow a mathematical formalization of the observational method. Meaning that you see here that just after the first excavation, before I put my strut here, I have computed a maximal horizontal displacement here of 7 millimeters. Now, if I have an inclinometer, and this inclinometer tells me that this is not 7 millimeters as I computed, but this is actually 5 millimeters. So I can use this new information. I can also put an observation error here. And my model will learn from this new observation and will update the input distributions. So you see that at first, I was computing something which was close to 7 millimeters for this horizontal displacement. And now, after the measurement, with the little error in the measurement, I'm closer to 5, and I have drastically reduced this distribution. So this helps me with the Markov chain Monte Carlo algorithm to update the distributions of my input. If I update these distributions, then I can rerun the probabilistic analysis, the reliability analysis, and then what do I get? I get that the probability of exceeding these 25% is no longer 20%, but with this new information, it's 3%. So I'm very happy. I go to my client, and I tell him I don't have to put much more money in his project, and that everything will be all right. But now I have some, it's just not me who says, okay, I measured 5 millimeters instead of 7, so it's going to be good. I have a mathematical way to compute this probability of failure, and it dropped from 20 to 3.